In this video, we're going to take a careful look at what it means for a sequence to converge. And I know we touched on the notion of what it meant for a sequence to converge in the last video. But in order to really be able to work with sequences, we have to actually be able to evaluate those limits. And so I want to discuss what it means for the limit of a sequence to converge. So we're going to start off first with the basic definition. We're going to say if we have some real sequence x sub n, it converges to some real number c if the limit of the sequence terms as n goes to infinity is equal to c. And it's important to understand what this limit means. One thing that it doesn't mean, and people often think it doesn't mean that the values are getting closer to c. It doesn't just mean that. Here's kind of an example to illustrate what I'm trying to say. Suppose we look at the sequence c plus 1 over n. Okay. Notice that as n gets larger, the sequence terms do get closer to c. But the sequence is not said to converge to c because the key point is that I can't make the sequence terms get arbitrarily close to c. In other words, I can't make them get as close as I want them to. Because you notice that the sequence terms are always a distance of at least 1 away from c. And so the first condition for a limit to exist is that no matter how close you choose to be to c, this is what we call epsilon, the distance away from c, we have to be able to find some term in the sequence that is at least that close to c. That's the condition that the absolute value of the sequence term minus c is less than epsilon. Remember, the absolute value is the distance between 2 points. Okay, so we're saying that we have to be able to find some term that is a distance epsilon from c for any given epsilon. But the full statement for a limit is actually a little stronger than that, because what it says is that in order for a limit to exist, no matter what epsilon you give me, I have to be able to show that there is some term in the sequence such that all of the terms past this specific term all lie within epsilon of c. So let me illustrate that. So you give me any distance epsilon, and the idea here is that I have to be able to come up with some term in the sequence such that all the terms in the sequence past that one all lie within epsilon of c. That's the idea behind a sequence. So to kind of recap, for every epsilon greater than 0, that is, if you tell me how close you want to be to c, there is some natural number n, capital N. This is the term in the sequence. This is the place of that term in the sequence, such that for all small n greater than or equal to capital N, in other words, for all the terms in the sequence past x sub capital N, all of those terms lie within epsilon of c. That's the condition that the absolute value of the difference of xn minus c is less than epsilon. Okay. And though this is what we mean by the limit of a sequence converging to a number. And it's very important to understand every part of this explanation. And I'm going to illustrate with some examples in a second. Two things that you always want to remember is that generally that capital N, that term in the sequence, okay, is going to be dependent upon epsilon. All right. So you give me epsilon and I have to find some position in the sequence, and of course that's going to depend on epsilon in general. And so sometimes people write it as n sub epsilon. I'm not going to do that, but you should realize that. The other thing, again, I'll remind you of is that that number c has to be a real number. Okay, so we cannot talk about a sequence converging to infinity. Okay, we just don't talk that way. And so we use this notation when we want to say that it converges to C. We use this arrow. We say the sequence arrow C. That means the sequence converges to C. Sometimes people will also add as n goes to infinity, but it's kind of redundant since that's basically in the definition of what it means to converge. And again, I'll remind you that a sequence can only do one of two things. It can either converge or diverge. So any sequence that does not converge diverges. And we saw before that one way it can diverge in that example with the arithmetic sequence is that it can become an infinite limit. Okay? But it's also true that a sequence can diverge if that limit doesn't simply exist. And that was that oscillating sequence that we saw. Let me illustrate the definition by doing an example. So let's suppose we want to prove that the sequence 1 over n converges to 0. So here's going to be our proof. We're going to say, okay, consider the real sequence. Defined by 1 over n. And we always start the proof by let epsilon greater than 0 be given. So we're going to say, okay, suppose that we have any positive distance. Now we want to find that sequence term. So what are we really trying to show? We're trying to find, here's kind of our goal in a sense, is we want to find some capital N such that x sub capital N, which is 1 over n, is less than epsilon. Well, it seems we should be able to find that, right? Because one thing we do know is we know that for any epsilon greater than 0, we can always find some capital N greater than 1 over epsilon. Okay? This is actually a fact from real analysis. It's called the Archimedean Property of the reals. It says that for any positive real number, we can always find a natural number greater than it. But of course, we kind of know this intuitively, right? And so given that this is true, we're just going to choose capital N to be greater than 1 over epsilon. And so it automatically implies that 1 over n is less than epsilon. And this capital N is going to do the trick, because now if we consider all the sequence terms past that, so now if we let n be greater than capital N, what we find is that x sub n minus 0, which is equal to 1 over small n, is going to be less than 1 over capital N, which is less than epsilon. So that does the proof. So now we can go ahead and we can write the proof formally. Okay, this was kind of the idea of what was going on, but now we're ready to write it up. And now we're going to say choose capital N, a natural number, such that capital N is greater than 1 over epsilon. Then we know that this is true. Therefore, for every n greater than or equal to capital N, which proves And that's our proof. And we can actually adapt this to slightly more exotic situations. Let me just kind of show you a little twist on this. Suppose we wanted to prove something a little more general. And I'm just going to kind of sketch this, but you'll get the idea. Suppose we want to prove that 1 over n to the p converges to 0, where the exponent p is greater than 0. Here's going to be our proof, okay? So we're going to let the sequence be defined as 1 over n to the p, where p is greater than 0. And now I'm going to let epsilon greater than 0 be given. And again, we're going to kind of work backwards. This is how these proofs are sometimes. What do I want? Well, really what I want is I want to find some capital N such that this is true. This is my goal. And so now I'm just going to work backwards. I'm going to take the pth root, and I'm going to essentially solve for capital N. And when I do, I'm going to find out that this is basically equivalent to choosing capital N to be greater than this. And now I can argue this same sort of way. Once I figure this part out, then I know how to do this proof. So I'm going to say choose capital N, a natural number, such that N is greater than 1 over the pth root of epsilon. Therefore, for every n greater than or equal to capital N, I know that the difference of the sequence terms with 0, the absolute value of, is just going to be 1 over n to the p, which is going to be less than or equal to 1 over capital N to the p, which is less than epsilon. And that completes our proof. Okay? And so this kind of will give you an idea of how we're going to actually use the limit definition to prove that a sequence converges to a particular value.